Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to discuss about the module Photolithography from the paper Semiconductor Materials and Devices. So students, from this module you may get to know about the following. First of all, you will get the introduction of photolithography. What is photolithography and why it is named so? Secondly, you will study about the process of photolithography, that how the process of photolithography is performed. So before getting into this module in details, let us have a brief introduction. The fabrication of an integrated circuit or IC requires multiple physical and chemical processes to be executed on a semiconductor substrate. For example, silicon is also one of the semiconductors which is used as a substrate. In general, the various processes used to manufacture an IC fall into three categories. First one is the film deposition. Second category is patterning, and third one is the semiconductor doping. Conducting such as polycrystalline silicon and aluminium, as well as the insulating films, for example various forms of silicon dioxide, silicon nitride and others, are used to connect and isolate transistors and their components. The conductivity of the silicon can be altered with the application of voltage by selectively doping various regions of the silicon. By creating structures of these different components, millions of transistors can be fabricated and assembled together to form the complex circuitry of a modern microelectronic device. The most fundamental of these processes is lithography, that is, the formation of three-dimensional images for subsequent transfer of the image pattern to the substrate. Photolithography, as its name suggests, consists of the word photo and lithography, where photo means light and lithography is further another word from Greek where lithos means stone and graphia means to write. So we can say that lithography is to engrave some pattern or write something on stone, but the same word is used for incising some pattern on desired substrate like silicon, corning, quartz, etc. Photolithography is to incise the desired pattern on the desired substrate using light. For example, ultraviolet rays. The patterns are formed using photoresist, which we will discuss later in this module. Also, the termed as optical lithography or UV lithography, it is the process used in microfabrication to pattern parts of thin film or a substrate. Light is used to transfer a geometric pattern from the photomask to a light sensitive chemical called as photoresist or simply resist on the substrate. In this way, a photoresist pattern is incised on the substrate, which may be useful incising pattern of any desired material like aluminium, gold, copper, platinum, etc. on the desired substrate. let's discuss the process steps of lithography. In typical photolithography, basically we start with the wafer already coated with the material to be patterned. Photoresist is coated using spin coating technique and allowed to bake for some time such that the solvent can be evaporated, followed by the UV exposure. The figure given on next slide presents the schematic for the following process steps in photolithography. On UV exposure, the properties of the photoresist got changed and exposed part get dissolved in developer for the positive photoresist, whereas unexposed part get dissolved in developer for the negative photoresist. Since we have transferred the pattern from mask to substrate, now the part which got dissolved in developer can be etched easily using chemical etching or plasma etching, keeping the undissolved part unaffected since it is protected by the photoresist. The photoresist which was protecting the patterns can be easily removed using chemical treatment or plasma etching. There are some materials which cannot be etched easily are patterned using Liftoff technique. In this technique, negative image of the pattern is incised on the wafer before depositing the material. The material is deposited after this such that the material get deposited on the desired places where there is no photoresist and deposited on the photoresist layer where the pattern is not required. On dipping the wafer in suitable chemical photoresist got dissolved, taking with it the material layer from the unwanted places. Hence this process is called as liftoff. So next we will discussing about the photolithography steps in detail. Here the etching part is discussed in detail. Since liftoff is same as etching only except the ordering of steps, so only a brief introduction of liftoff is given in the end. So now let's see the flow chart of steps followed by the detailed description of each step. So you can see the schematic for the photolithography process given in the figure. The first step is the cleaning of substrate, then the spin coating of photoresist, then pre-baking, after that UV exposure, after the exposure we develop, then post-baking, then etching and finally stripping. So now let's study these steps in detail one by one. Surface preparation. Surface preparation is the most important and most crucial step to start with the photolithography. It is aimed to improve the adhesion of the photoresist material to the substrate. This is achieved by one or more of the following process involving substrate cleaning and dehydration bake. The substrate cleaning is used to remove contamination. Substrate contamination can be in the form of particulates or a film and can be either organic or inorganic. Defects in the final resist pattern are a consequence of a particulates, whereas film contamination can cause poor adhesion and subsequent loss of line width control. Particulates generally arise from airborne particles or contaminated liquids, for example, dirty adhesion promoter. Therefore, substrate cleaning is very much necessary before photolithography. For chemical cleaning, RCA1, RCA2 and piranha cleaning are used to remove all the organic and inorganic impurities. Also, various other solvents like tetrachloroethylene, acetone and isopropyl alcohol are also used for cleaning different substrates like glass, silicon and sapphire, etc. Piranha cleaning is first used to clean the wafers generally, which is a mixture of sulfuric acids and hydrogen peroxide in 1:1 ratio. It removes the organic and inorganic contaminations from the wafer. RCA1 is a mixture of deionized water, is to ammonium hydroxide is to hydrogen peroxide in the ratio of 5:1:1. Wafers are dipped in the RCA1 solution at 80 degrees Celsius typically for 10 minutes. RCA1 cleaning helps to remove the organic residues and is also very effective in removing particles from the surface. Subsequently, deionized water is used and the wafers were dried with a jet of dry nitrogen gas, whereas RCA2 cleaning removes ionic and metallic contaminations present on the surface of the wafer. RCA solution consists of the mixture of DI water, hydrochloric acid, hydrogen peroxide in 5:3:3 ratio at 70 degrees Celsius. The cleaning is done for 20 minutes and finally the wafers are rinsed in DI water and dried finally. These treatments result in the formation of thin silicon dioxide layer in case of silicon wafers. It can lead to recontamination since the bare silicon surface is very effective. So to remove the native oxide from the silicon wafer, wafers are dipped in the solution of hydrogen fluoride and deionized water in the ratio of 1:20 for 5 to 10 seconds. Again, the wafers are to be rinsed in DI water and dry with dry nitrogen gas. Spin coating of photoresist. Resist formulation may generally consist of first, film forming resin, second, solvent, third is sensitizer or photo initiator or photoacid generator, and the fourth one is additives. The dried film coated form a solution containing the above ingredients undergoes changes when exposed to radiation of a certain wavelength or electrons or even ions. This exposure alters the solubility in the developer of the exposed areas relative to the unexposed areas. If the resist prints in the negative tone, the exposed areas are hardened, whereas positive tone resists are made more soluble in the developer solvent by the exposure. The changes in the exposed areas are due to some chemical reactions brought about by the adsorbed radiation. When the surface is cleaned, the photoresist is applied using spin coating technique. A viscous liquid solution of photoresist is dispensed onto the substrate and the substrate is spun rapidly while being coated with the photoresist such that it bonds uniformly to the surface. This uniformity can be accounted for using a fluid mechanical model which shows that the resist moves much faster at the top of the layer than at the bottom, where viscous forces bind the resist onto the wafer surface. Thus, the top layer of the resist is rapidly expelled from the wafer edge while the bottom layer still moves slowly and radially along the substrate. In this, extra resist is removed, leaving a very smooth and uniform layer of photoresist. The next is the pre-bake. The pre-bake is a simple process where the surface is heated in the convection oven or through a hot plate placed below it. The purpose of this step is to evaporate the excess coating solvent and to compact and harden the photoresist such that the adhesion of photoresist increases and the film got less susceptible to the contamination. Alignment and exposure. After baking the wafer must be aligned correctly with respect to mass such that we get the pattern of the mask on wafer at desired position. This procedure is accomplished by a micromechanical controller provided on the mask aligner using certain marks pre-printed on the mask or by using an automatic pattern recognition device. Mask aligner. Mask aligner is one of the important instruments that perform one-to-one exposure for the microstructuring in the lithography process. The first mask aligner was developed by Carl Zeiss in 1963 for the fabrication of transistors at Siemens in Munich, Germany. Basic principle of mask aligner. The principle of the mask aligner is based on the illumination of a photomask which is brought into the contact or kept at a small proximity distance from a photoresist coated wafer. This technique can be classified as contact or proximity printing depending on whether the mask is in direct contact to the wafer or there exists a proximity gap between the both. Furthermore, the contact mode is divided into two modes. First, the soft contact and second, the hard contact. In soft contact, the substrate is brought into contact with the mask by a predetermined force during the time of exposure, whereas in hard contact, an additional upward force is given to the wafer by inletting nitrogen purge into the system to provide better contact. Exposure of UV radiation to the wafers can be carried in different contact modes as shown in the given figure. So the given figure shows the different contact modes used in mask aligner: soft contact, hard contact, vacuum contact, low vacuum contact, proximity contact and flood exposure. Hard contact is preferred over soft contact in doing alignment for pattern line width less than 10 micrometer. So the different ways adopted for alignment are given in the given figure. The two most commonly used alignment types are top side alignment or TCA and the backside alignment BSA, which are shown in the given figure. In the top side alignment or TSA, at least one time patterned wafer is aligned with new photomask from the microscopes given on the top side of the system. On the other hand, in BSA, the patterned wafer is aligned from the microscopes given at the bottom of the system. In BSA, an image of the photomask is captured first and then the backside of the patterned wafer is aligned with the grabbed image. After alignment, a high intensity ultraviolet lamp is used for exposure of photoresist coated on the wafer through a photomask to imprint the pattern given on the photomask. So in the figure given here, you can see the isometric view of the top side alignment and the back side alignment system. After the alignment, UV light is allowed to fall on the substrate as shown in the above given figure 5 through a mask containing the desired pattern for the optimized time, which will be different for different substrates. In the given figure 4, you can see the photograph of mask aligner. The next step is development. A post-exposure bake or PEB is carried out before developing the wafer so that the standing wave phenomena caused by the destructive and constructive interference patterns of the incident light can be reduced in order to get a smooth pattern. Upon exposure to light, a chemical change in the photoresist occurs, which allows some of the photoresist to be removed by a special solution called developer. During the development step, chemicals are applied to the surface, causing either a reaction with photoresist. Positive photoresist becomes soluble in its corresponding developer when exposed, while in the negative photoresist, unexposed regions dissolve in its corresponding developer. The figure given here, figure 6, shows the schematic after the removal of UV exposed photoresist. The next step, which is the sixth step, is post-bake. The post-bake is done to stabilize and harden the photoresist. It also removes any remnant developer. The resulting substrate is then hard baked, typically at 140 degrees Celsius for 20 minutes. The remaining photoresist solidifies on hard bake so that it is able to withstand etching and does not get damaged during etching process. Next step is etching. Etching is an essential step during microfabrication. The process of etching involves both chemical and mechanical mechanisms leading to the removal of the material which is not protected by the photoresist. Etching can be done either in the form of wet etching or dry etching. Wet etch is perhaps one of the simplest form of etching method. It requires an etchant solution such as an acid that removes the underlying film, reacting chemically, leaving the photoresist intact. This etching is isotropic and thus can lead to damage of pattern below the photoresist also. So, an isotropic etching can be used as substitute in which directionality is induced into the etch process. In this case, wet etching does not serve the purpose, then dry etching or plasma etching comes into picture. In plasma etching, the etchant is replaced using plasma, that is an ionized gas. An electric field is applied that causes the ions to be accelerated downwards towards the wafer. The resulting etch is a mixture of both chemical etching that occurs due to reaction of the film with the plasma and physical sputtering due to the bombardment of the ions hitting the wafer. The chemical character of the etch leads to the etching sensitivity of the film with respect to the resist and with respect to the substrate below the film. Plasma etching is very directional but not very selective. Reactive ion etching is another way of etching that merge both effects to give better selectivity and directionality. The eighth step or the next step is the stripping, which is the removal of photoresist. After the imaged wafer has been pattern transferred, the remaining photoresist must be removed. There are two classes of resist stripping technique. First is the wet stripping, that is done using organic or inorganic solutions, and second one is the dry stripping. In the end, since we have got our desired pattern of the desired material beneath photoresist which is no longer required, it must be removed from the substrate. To remove the excess photoresist, acetone is used. Also, we can remove the photoresist using oxygen plasma. The figure given here, figure 8, shows the schematic after the removal of photoresist from the substrate. The next step is the Liftoff process. There are some materials which are not easy to be etched. In that cases, we pattern the photoresist on the wafer where we don't need the pattern of desired material such that it leaves the desired places uncoated with the photoresist using dark field mask. Now, we can coat the substrate with desired material and material from the undesired places can be removed using lift-off technique. On dipping the substrate in acetone, it will dissolve photoresist beneath the undesired places, removing them. So students, let us summarize what we have learned in this module. We learned about the complete process of photolithography for the development of microstructures, along with the detailed description of each and every step along with its schematic diagram. Thank you.